Our first talk is from Lilian Cheng from UC Irvine, and her talk is titled Travel Direction as a Fundamental Component of Human Navigation. Oh. So Lilian, the floor is yours.
Okay, thank you. Can you all see my screen now? All right.
Yes, we can.
Started. Hello, everyone. I'm Lily Chen from the University of California, Irvine. And today I'd like to talk about my study, Travel Direction as a Fundamental Component of Human Navigation. Imagine you're on your way walking to a Starbucks, and you can hear birds singing up in the tree and feel the breeze touching your skin. And suddenly, you notice a bunny running by. Where did it go? You turn your head to follow the bunny running and hiding into a nearby bush, while your feet are still walking toward your destination. In this case, where you are facing toward and where you are moving toward are both part of your sense of direction, but they represent different spatial information. Head direction refers to where someone is facing toward, while travel direction refers to the direction of one's body movement. In daily life, people usually conflate the two directions, thinking that where we are facing toward is where we're going. But as you have seen in the bunny example, these two factors can offer different spatial information. Extensive studies have focused on head direction cells in the brain. Although head direction has been found to be a crucial part of human navigation, travel direction might be more important to determining the travel trajectory. However, it is unclear whether travel direction plays a primary role in navigation. As travel direction forms a travel trajectory together with speed and time, we hypothesize that travel direction is a fundamental component of the internal representation system of human navigation. To test this, we adopted a visual motion adaptation paradigm, much like the waterfall illusion, which you can try yourself by staring at it. In motion adaptation, neurons selected for visual motion features are serialized to adapt to visual stimuli that corresponds to its selective firing properties after prolonged exposure. This adaptation often results in a decrease in the neuron responsiveness to the same stimuli compared to an unadapted response. This is represented at a behavioral level as a motion aftereffect, such that a stationary stimulus will appear to move in the opposite direction to previously viewed motion, just as you perceive the waterfall going up once the video paused. Therefore, we used a motion adaptation paradigm to probe for selectivity of travel direction. In our experiment, we predicted that navigators adapting to a travel direction will show an increase in reporting the opposite direction. We carried out our study in a virtual environment, which includes a virtual hallway and two reference points indicating cardinal directions, a sun and a moon, that located at the two ends of the hallway and were said to be infinitely far. Our experiment had two sessions. Each session was conducted on a separate day. One session was an adaptation session. The other session was a control session. The order of the two sessions was counterbalanced among subjects. For the adaptation session, half of the subjects were randomly assigned to adapt to the moon direction, and another half were assigned to adapt to the sun direction. Control conditions were the same across all subjects. Now, let's look at the adaptation session. In the adaptation session, we first adapted people to visual self-motion in one direction in a virtual hallway, either towards a sun or a moon. The head direction was reversed occasionally to be dissociated from the travel direction, while travel direction during the adaptation phase remained constant in one direction. Changing head direction precluded optic flow from contributing to any observed adaptation effects. We then tested people with a series of visual back and forth movements toward and away from the initial travel direction. The head direction also reversed occasionally during test as well. At the end of each test trial, we asked subjects to report their net travel direction. We varied the percent of movement toward the sun direction during the test phase between 20% and 80%, allowing us to measure psychometric functions for perceived travel direction. After each test trial, we presented a 10-second long top-up adaptation to maintain the adaptation during testing. And after each top-up was another test phase trial, followed by another top-up adaptation, and then a test trial, so on and so forth. Now, let's look at the control session. In the control session, the viewer was stationary during the adaptation phase. To match the adaptation session, head direction in the control session also occasionally reversed. The test phase of the control session was the same as in the adaptation session. We compared the adaptation session with the no-adaptation control. When using the percentage of the actual and reported movement to the adaptation direction as x and y-axis, we predict a line for the control session where the reported rate increases with the actual rate. For the adaptation session, we predict the adaptation line to be a line that is shifted to a lower position than the control line because people tend to have weaker response to the adapted stimuli. Here are the results for the control session, shown in red, and the adaptation session, shown in blue. We found a difference between the people's report of the net change of travel direction in the adaptation session and in the control session, as you can see in the difference between the two lines. The results indicate a motion after effect of travel direction, suggesting that travel direction is a fundamental component of human navigation. Interestingly, subjects had a higher frequency of reporting net travel toward the adapted direction, indicating that the after effect is opposite to the traditional motion after effect. We have run additional controls and conducted additional analysis, indicating that this is not driven by response bias or other factors. And I'm happy to answer questions about this in the discussion. Overall, this study suggests that travel direction is a fundamental component of human navigation. We will next investigate whether these signals can be detected in the brain during fMRI imaging. If you'd like to know more details of the study, please scan the QR code for a poster version of the study. Thank you for your listening, and I'd like to take questions.
All right, thank you, Lily. That was a really great talk, super clear, and I especially appreciated your lead in with the hypothesized results. I thought that really was helpful for me to understand. So I have a few questions, but if anyone in the audience would also like to ask a question, please feel free to post in the chat or in the Q&A. So one of my questions was more of just a comment about how interesting it is that you point out that travel direction and head direction are often decorrelated. I think it's especially important in the study of human navigation when we use virtual navigation. I'm reminded of like how when we play video games, for example, and also navigate on like a desktop computer, that is a specific time when often the facing direction can be decorrelated from the head direction. So like like many times you would be strafing as a character more often in a video game than you would in real life. And so I was wondering whether you guys have considered how frequent, like any kind of naturalistic behavioral analysis or in either humans or animals to look at how often in like real world navigation heading direction really is decorrelated from facing direction. Do you have a sense of that?
Yeah, I think part of the reason for us to do it in VR is just because it's easier to control it. And yeah, in real life, people do look around, but not like looking around, like going like a crab way, only looking in the same direction and going in the other direction. It's hard, it's not very natural for people, but I think maybe with a more immersive VR headset, it could be possible to conduct, or maybe like a well-round treadmill that people can just
Yeah,
walk
actually,
on. Yeah.
it was, oh, sorry, my headphones have dropped off for a second.
Yeah.
Yeah, I actually have I'd been speaking recently with somebody who works with an omnidirectional treadmill, and they said that one of the nice things is that people behave more similarly to real world navigation, where they're like they realign themselves before they make a movement, unlike in like a video game task where they can easily like shuffle. And like a lot of times, I think about the times when people do turn their heads and navigate when they aren't looking in one direction. And it's similar. I think your example of the rabbit is a good one, where you're like tracking something. And that seems to generally be the case. It's like I can think of two examples off the top of my head, which is the example like you did with the rabbit, or like generally tracking something, or in sporting events when you might be tracking something too. So it seems like that's part of the behavior. My other question was leads in nicely to your future direction, which was whether you think that this is going to be a separate neural system that underlies or underpins this travel direction maintenance from the heading direction system, or the and what systems you might expect that to be. Like where do you think this is going to be coded?
Yeah, so by saying heading direction, it's actually already conflating the head direction and travel direction. So
right.
So let's separate them. So
sorry. Yeah, that, my question was poorly phrased.
Yeah. Yeah, for the head direction. I know what you're saying. So yeah, so I think because people have conflated it before, so it is very likely that the head direction system that we already have found, that like subiculum, thalamus, retrospinal cortex, these regions could have some overlap with the travel direction system, or travel direction system is a subset of it, like a special case of it. Because I think travel usually has to involve motion, so I think the high-level visual motion system could also play an important role here. So there should be some interaction where different parts of visual system and like directional system involved in it. That's what I'm thinking, but I'll see what I can find.
Cool. Well, I'm really excited to see the next phase of the results. So thank you very much for that talk.
Thank you.
So with that, I think we'll move